Hi, and welcome back. After having introduced in the previous lessons the fundamental concepts and developed the fundamental equations that we need in order to describe the thermodynamics of mixtures, we are now ready to enter the art of modeling. Let's start, and let's do it by getting back to the gas-liquid chemical equilibrium equation with which we had closed the previous lesson 3. Once again, this expression equates the fugacities of a component in a liquid and in a gas phase. We have seen that equality of fugacities is equivalent to equality of chemical potentials, and that the latter corresponds to energy minimization. If our problem is that of determining the equilibrium conditions for a given pressure-temperature pair, then the energy which is minimized by equality of chemical potentials is Gibbs energy. In turn, that corresponds to maximization of system entropy, therefore to the condition of equilibrium prescribed by the second law of thermodynamics. That's a condensed summary of what we have seen in all previous lessons. We know all of the terms that appear in the equilibrium equation, at least in their general meaning. The fugacity coefficient in the gas phase, phi, and the activity coefficient and reference fugacity in the liquid phase, gamma and F0. Temperature and chemical composition, which do not appear explicitly, contribute together with pressure, which is also explicit in the equation, to define all of those terms. The remaining terms are the mole fraction of the component in the gas and liquid phases, Y and X respectively, according to the convention that I use. Y for mole fractions in the gas phase, and X for mole fractions in the liquid phase. The first relevant element to keep in mind here is that once a new phase is formed, all of the components in the mixture are partitioned between all of the phases in the system. Thus, as soon as a gas phase starts forming in a liquid body, such as a magmatic melt, you will find in the gas phase, here represented by the green bubbles, whatever component is also present in the liquid phase. That means that the gas phase coexisting with the liquid magma is not only made of just the classical volatile components, such as water, carbon dioxide, sulfur, and a few others. Instead, the gas phase contains also some quantities of sodium, potassium, silicium, aluminium, and whatever else can be found in magma, such as gold, uranium, platinum, leads, and so on. Certainly, most of those components are contained in the gas phase in so small quantity, so little quantity, that for any practical application, it's totally fine to neglect them. Unless, of course, we are interested in exactly the behavior of such trace elements. In fact, for many applications, we can safely neglect even some of the most volatile components, such as the halogens, chlorine and fluorine, and often even sulfur. How many and which volatile components we should account for in our thermodynamic modeling? That depends on a number of factors, which include their relative abundances and the problem that we are dealing with. Clearly, if we want to interpret the variations that we are observing at a given volcano in terms of sulfur carbon ratio in the volcanic gases, we must, as a minimum, account for both carbon and sulfur. As a rule of thumb, we should always include at least water, the most abundant volatile in magmas, and among the most soluble volatiles, and carbon dioxide, the second most abundant volatile and the least soluble of the magmatic volatiles. In fact, the very low solubility of carbon dioxide in magmas makes this volatile component to exert a strong control on gas formation and evolution in magmatic systems. We will see it in a few slides, and you will be able to experiment it yourself when doing exercises inside Unit 3. By now, just take the concept that if carbon dioxide was not present in magmas, then we would likely see much less volcanic activity on Earth, and the evolution of the atmosphere and the oceans would have been different. The arguments of both concur to explain why a large part of the modeling studies on volatiles in magmatic systems concentrate on water and carbon dioxide. Because of its extremely small solubility in magmatic melts, including or not including carbon dioxide, deeply changes the gas saturation conditions and the pressure saturation relationships. There is no other volatile component with so deep effects and consequences. And besides that, carbon dioxide is, after water, the most abundant volatile in magmas. Okay, I said that water and carbon dioxide have been largely investigated in the magmatic literature. Still, the vast majority of laboratory experiments refers to conditions where only one of these two volatile components is present. That reflects the need to understand the behavior of each individual volatile component in magmas before the complexities of multi-component volatile saturation are considered. We will see now that there is a substantial difference when dealing with the equilibrium involving only one volatile component or more than just one volatile component. Okay, I say that water and carbon dioxide have been largely investigated in the magmatic literature. Still, the vast majority of laboratory experiments refers to conditions where only one of these two volatile components is present. That reflects the need to understand the behavior of each individual volatile component in magmas before facing the complexities of multi-component volatile saturation. However, there is a substantial difference when dealing with the equilibrium involving only one volatile component or more than just one volatile component. Again, remember that the gas phase is always made of all of the components that are also present in the liquid phase. However, such components can be present in vanishing amounts, and we can often safely approximate the conditions by referring to only the more volatile species which are present in magmas. If we refer to only one volatile component, for example, only water or only carbon dioxide, then the mole fraction of the component in the gas phase takes the value of 1, because the gas phase is made of only that volatile component. Let's see the case for water. Here is the chemical equilibrium equation for the case where water is the only volatile component in the system. Let's have a closer look at it. There are the usual terms that we know already, except the mole fraction in the gas phase, which is equal to 1 and not reported here. And there is, here underlined in red, the mole fraction of water dissolved in the liquids. That quantity, mole fraction of water in the liquid phase, is the only unknown in the equilibrium equation. Of course, we have other quantities that must be defined, such as the activity coefficient and the reference fugacity of water in the liquid phase, and the fugacity coefficient of water in the gas phase. Still, those quantities do not bring in any additional unknown. Provided we know how to express them, what we will see one by one in the next lessons, we are left here with one equation and one unknown. The system is therefore entirely defined, and we can solve for the unknown represented by the mole fraction of water in the liquid phase. For example, Let's assume we are doing the calculations for a synthetic laboratory melt with composition corresponding to albite, and for specified pressure and temperature, say 200 megapascals or equivalently 2 kilobards, and 1400 Kelvin. After solving the equilibrium equation, we determine the amount of dissolved water in that liquid at that pressure and temperature. That amount is termed the solubility of water in the albidic melt at 200 megapascal and 1400 Kelvin. The solubility of a volatile in a melt refers to an end-member condition where the gas phase is made of just that pure volatile component. It is a thermodynamic property of a melt, meaning that for any given melt at any given pressure and temperature, the solubility of each volatile is entirely defined. The solubility of a volatile component in a melt at given pressure temperature conditions is the amount of that volatile component that is dissolved in that melt at equilibrium with a gas phase made of that pure volatile component at the specified pressure and temperature conditions. The situation is totally different if we have more than just one volatile component in the gas phase. Let's see it for the two major volatile components, water and carbon dioxide. Here are the two corresponding chemical equilibrium equations. The first one for water, but the second one for carbon dioxide. Now the gas phase is made of water and carbon dioxide in a proportion that we need to determine by solving the equations. How many unknowns do we have in this case? We have four unknowns, namely the mole fraction of dissolved water and the mole fraction of dissolved carbon dioxide, the mole fraction of water in the gas phase, and the mole fraction of carbon dioxide in the gas phase, the quantities which are undersigned in red. We have four unknowns and only two equations. Contrary to what we have seen before for the case of a pure volatile component, now the system is not entirely defined by the equilibrium equations. Instead, we need two more equations. Well, the first one is obvious, because we are considering only water and carbon dioxide as volatile species. The gas phase is made of only water and carbon dioxide. Therefore, the mole fractions of the two volatile components in the gas phase sum up to 1. That is what this mass balance equation says. We still miss one other equation that comes from another mass balance. This one says that given certain amounts of water and carbon dioxide in the two-phase magma, no matter how they partition between the gas and the liquid phases, such amounts must be maintained. In other words, this mass balance equation states that upon equilibrium, the mass of water and that of carbon dioxide are not created nor destroyed. They are just partitioned between the gas and the liquid phase. The superscript T refers to the total amounts of water and carbon dioxide in the two-phase magma. This quantity do not appear in the case on the left, the case where we defined the concept of solubility, which refers to equilibrium with a pure component gas phase. Now, in multi-component volatile conditions, the equilibrium also depends on the total abundance of each component in the system. That's a totally different situation. Consider again the case of the albidic melt at 200 megapascal and 1400 Kelvin. By solving the equilibrium equation for the pure water case and for the pure carbon dioxide case, we can determine the water and the carbon dioxide solubilities. However, if water and carbon dioxide are both present in the magma, their dissolved amounts also depend on how much water and how much carbon dioxide are present, and the dissolved amounts will be in general different from the corresponding solubilities. In fact, we refer in this case not to solubility, which refers instead to equilibrium with a gas phase made of the few volatile components. Here we refer instead to saturation. The saturation conditions is not a property of a melt, as it does not only depend on pressure, temperature, and the melt itself. It also depends on the total amounts of each volatile component. Let's see it with a practical example. This figure shows calculations made with SolveCAD that you will largely use in Unit 3. On the horizontal axis, I have reported pressure in megapascal, or if you are more comfortable with kilobars, just divide by 100. So 200 megapascal becomes 2 kilobars, and etc. On the vertical axis, I have reported the amount of water dissolved in the liquid phase, which is, for this example, a shoshonitic mat from the Campi Flegrei caldera close to Napoli, southern Italy. That's not important, it's just an example. For any calculation shown here, the total water content is assumed to be 3.58%, the same for all computations. The numbers in colors corresponding to each curve indicate instead the total carbon dioxide content. So the leftmost curve in black refers to a total carbon dioxide content equal to 0. That is, therefore, the water solubility curve. This curve continues in principle above the 3.58% content, but because I feel that that's the maximum amount of water available in the magma, when that total amount is entirely dissolved in the liquid, there is nothing else to dissolve again. And from there on, the dissolved amount does not change, even if the pressure increases. So the solubility curve of water becomes a flat curve. Here we reach 3.58%. There is nothing else to dissolve, and the curve becomes flat. The calculation tells us that such a volatile saturation condition, that is the point where gas bubbles start to form, is achieved at 91.5 megapascal, or roughly, taking an average rock density in the upper crust equal to 2,500 kilograms per cubic meter. That would correspond to about 3.7 kilometers depth. Let's now consider the next curve on the right, that is, the red one. In this case, there is also carbon dioxide in the system, although in the modest total amount of 0.58%. Although we plot the amount of dissolved water, the red curve does not follow the water solubility curve in black. It shows instead the multi-component volatile saturation conditions corresponding to the specified total amounts of water and carbon dioxide. In the absence of carbon dioxide, the black curve 91 megapascal pressure was enough to entirely dissolve 3.58% water in the melt. Now, with the addition of only 0.58% total carbon dioxide, in order to dissolve that same amount of water, we need a pressure as high as 523 megapascal, reported here in red, nearly 6 times larger than for the pure water case. The presence of just a small amount of carbon dioxide in a total mass ratio of 1:7 with water completely changes the situation. Now a gas phase would start forming not at about 3.7 kilometers depth, as for the black curve, but as deep as about 19 kilometers depth. In terms of magma and volcanodynamics, that's an apocalyptic difference, with huge consequences on the potential for magma to rise and eventually produce a volcanic eruption. If we increase further the carbon dioxide content of the magma, The pressure and depth at which a gas phase starts forming further increases, reaching 1 gigapascal or about 40 kilometers depth, when carbon dioxide is still in the reasonable amount of 2-8%, and going out of scale for this diagram for larger contents. In this example, the relevance of taking into account mixed volatile saturation conditions, and particularly the importance of accounting for the presence of the poorly soluble carbon dioxide components, emerges clearly. That makes huge differences. It totally changes the situation. Well, we are now ready to get into the various terms that make up the equilibrium equations, here reported once again in its most compact form. For each volatile component in the system, in the case that we will be looking at water and carbon dioxide, we need to find a way to express the fugacity of the component in the gas phase, the reference fugacity of the component in the liquid phase, and the activity of the component in the liquid phase. Once we know how to describe those quantities and their dependence on pressure, temperature, and composition, we can solve the equations and determine both solubilities and saturation conditions for water and carbon dioxide. That's what we are going to look at, starting with the next lesson, number 5. See you there.